right, today is going to be our last topic. I'm going to keep things short so that we can talk about any review items or whatever that we might need to discuss. So today we're going to be talking about feedback, trans impedance amplifiers. So in a feedback transimpedance amplifier, or let me start over here. In a transimpedance amplifier, we are amplifying a current signal and converting it into a voltage. So for a feedback transimpedance amplifier, that means our output of our open loop amplifier has to be connected in parallel to our feedback network because we are measuring or sensing a voltage at the output and applying feedback there. And on the input side, we are applying a feedback current signal, which means we also have to be in parallel on the feedback or on the input side of our amplifier. So this is going to be a parallel or shunt configuration. So what that's going to look like is this. Here we have our signal of interest, IS, that we are intending to amplify. Here's the input port of our open loop amplifier network, characterized by its open loop input impedance Ri. We know that we will have some error signal Vi and II available to us. On this side, we're going to have our dependent source. Since we are outputting a voltage signal, this is going to be a dependent voltage source. And it's going to be based on our open loop gain A1 and our error signal I sub I, because our input signal is a current, so that's why we're using the current error signal. Because we have a dependent voltage source, our open loop output resistance is going to form a practical voltage source with our dependent source, like so. And now we're at where our feedback will be connected, which are these terminals. I'm going to call this guy O and O prime. And this is where our output voltage is measured. For our feedback network, we're going to characterize this with a current source here at the input, having a value of K V out. And for port 2 of our feedback network is just going to be an open circuit. So now we'll go ahead and connect our feedback. And recall that we are supposed to be having a parallel connection. So I am connecting everything in parallel. Where this current right here is our feedback current IF. So everything on the top is once again our open loop amplifier. And everything that's connected on the bottom is, as per usual, feedback network. All right, so this is our ideal situation. Again, we're always trying to reconstruct this as effectively an equivalent circuit that buries the feedback inside. So our equivalent circuit diagram for this guy is going to look something like this. We have our input resistance with feedback here. We're going to have AF excuse me, IS here, I apologize. Here's R naught F, here are our terminals. And this is where our input signal IS is applied. And this is where our output voltage V out is measured. So to go from our general case to our equivalent circuit, we would then need to figure out what RIF is, what AF is, and what ROF is. We're not going to waste any time deriving literally anything because we know exactly how all of these things behave. So I'm going to ask you guys again for the fourth time, what should our gain with feedback or our closed loop feedback equation be? A1 over 1 plus K A1. Always that. Correct. And I didn't. Because I'm arrogant. All right. Our input resistance with feedback, RIF, which I guess I should be clear about where we are measuring that. That's going to be looking in through this terminal just as much as this is where we're going to look at our output resistance with feedback. So our feedback network is connected to the input of our open loop amplifier stage in parallel. So that will either boost or attenuate our input resistance. What's it going to be? Is it going to make it bigger or smaller? Smaller. So this is just going to be Ri divided by 1 plus K A1. And similarly, ROF is going to be RO divided by 1 plus K A1 because our feedback network is connected to the output of our open loop amplifier in parallel as well. So this is our analysis for the ideal case. Now we get to look at what happens when we have signal resistances, load resistances, and we assume that our feedback network is actually loading our amplifier. So under the constraint that we're using a practical system, we're going to have something that looks similar. We have our signal source I sub S, but now we're going to have some signal resistance or impedance to take care of as well, which I will call R sub S. So if we look in here, we see our input resistance with feedback. If we look in here, we just see the input resistance of the system where the signal impedance has been taken out. Just going to use a block diagram for our open loop amplifier. Out here, so just to be clear, this is S, this is S prime, this is O, our output, this is O prime. So if our load impedance is not infinite, it'll show up here, RL, and this is where we will now measure our new output voltage. So the output voltage will be the drop over the load resistance, which is exactly what we would expect for this kind of thing. Our feedback network, I'm going to draw down here. Again, it's just a simple block diagram. Here's port 1. Here's port 2. And we know that we're going to have parallel connections like so. I guess while I'm at it, this is RIF, looking in through here. Sorry, ROF, looking in through here is R out. Open loop, feedback network. All right, so this is our practical block diagram representation of our system. And now we'll go through the same few things that we had to do previously, figuring out what R11 is going to be, how much our feedback network loads the input of the open loop amplifier, figuring out what R22 is, which is how much our feedback network loads the output of our open loop amplifier. We can use simple network theory to figure out what our feedback factor is, and then from there we can construct our open loop circuit, which can then be used to determine our gain with feedback, our input resistance with feedback, and our output resistance with feedback. So we're doing nothing different than what we've done with the last 3 amplifier types. All right, so finding R11, if this is our feedback network, port 1, port 2, we're going to look in through port 1 with port 2 short circuit. And we're doing this because we're connected to the output of the open loop op amp open loop amplifier in parallel. Similarly, we can find R22 by looking in port 2. With port 1 short circuited, because again, we have a parallel connection. For our feedback factor, K, we look at our feedback network as per usual. We apply our output signal, which in this case is V out to port 2. And we look at what our feedback signal is, IF over here at port 1, with the constraint that the voltage drop across port 1 is 0. And our feedback factor K is defined as V out over IF, where V1 is equal to 0 volts. So we can see something actually pretty interesting right now before we even move forward and look at anything. Typically speaking, this feedback network here in the middle is just some combination of resistances and all that kind of stuff, right? That's all we've been dealing with. So what does it mean if V out has this polarity and IF has this direction? We're always going to have a negative feedback factor. So it seems like anytime we apply a current at our input, so when we have a current amplifier or a trans resistance amplifier, we're going to get negative feedback factors because of the way that we're accounting for things. So in order to have a negative feedback loop in our system, that means that our amplifier is also going to have to, the open loop amplifier is going to have a negative value for its gain. Otherwise, we're going to wind up with positive feedback, which is what we kind of looked at a couple of things with on, today is Wednesday, so Monday. All right, from here, we can construct our open loop amplifier circuit. That we analyze to figure out what our open loop gain A1 is. On this side, we are going to see RL in parallel with R22. This is where we measure our output voltage. On the input side, we are going to see RS in parallel with R11. And this is where we apply our input signal, I. And so from this, we know that our open loop gain A1 is going to be V out over II. So unit-wise, it should look like a resistance, which is why this is a trans impedance or trans resistance amplifier. So we now have all of the different bits and pieces to figure out AF, RIF. Oh, actually, just while we're here, looking in through this port gives us RI. Looking in here gives us RO, because we're going to need those later. So we now have enough information to figure out everything we could possibly want. So let's work one example problem and call it a day. All right. So our amplifier of interest is this guy. And when we're doing this problem, oh, actually, never mind. That was one I didn't do because it wound up being positive feedback. Hold on. I brought the wrong example problem down. That's okay. All right. This is the one that winds up having positive feedback, but we'll walk our way through it. Still illustrative of what's going on. All right. So let's work this problem with channel length modulation effects included. So let's say explicitly that lambda 1 isn't 0 and lambda 2 isn't 0. And one of the reasons I'm doing this is because I realized that I made a mistake on Wednesday, and this will allow me to rectify it. Okay. So our feedback network in this case, oh, actually I should define where my output signal is, which is here. So here is port 1, and over here is going to be port 2. Okay, so there are really two different ways that we can look at this, and in the grand scheme of things, it's going to make no difference whatsoever, all right? One way to look at things, we know that this is always going to be connected because this is effectively our ground node, or our reference for everything. So one way that we can look at this is that our feedback network is literally just the resistor R1. And the alternative way to look at it is that our feedback network is R1 between port 1 and 2, and R2 across port 2. Now, the reason why I say we can look at this both ways is because we could be treating that resistor R2 as our load resistance, because our output voltage is, by definition, the voltage drop between this node and ground, which is the voltage drop over R2. So either way works. We're going to wind up with literally an identical open loop circuit regardless of which way we look at it. Okay, so it doesn't particularly matter. So I will give us both. So R11, when we look at it with just resistor 1 as our feedback network, remember we're looking in through port 1 with port 2 shorted. So what should we see? R1. For our alternative Now include resistor 2 in the feedback network. Look in through one, short port 2. What do we see? Still R1. Okay, so nothing changed there. Let's see what we got here. R22. All right. So for R22, we look in through port 2 with port 1 shorted. So first case, ignore this blue resistor R2. What do we see? Just R1. Second case with the blue resistor included, what do we see? They're in parallel. So R1 in parallel with R2. So this is obviously different. Is that a problem? Well, no, right? When we break our feedback loop and we put R11 in parallel with IN and R22 in parallel between the output node and ground, if we only have it treated as R1, we still wind up seeing R1 in parallel with R22, which is why it doesn't remotely matter, okay? Our feedback factor, that's the wrong color. So this is what's going to happen. Let's see. We are going to apply a voltage V out here. And we are looking for this current IF here. So what do we see when R2 is ignored? What was that? That's incorrect. Use Ohm's law better, right? Our feedback factor is IF over V out. So how can it be R1? It has to be 1 over. We have a ratio. Let me write this down so I'm super clear here. IF over V out is our feedback factor. Dimensionally, it cannot have the units of resistance. It has to have the units of conductance, right? So we know that IF is negative V out over R1, which means IF over V out is negative 1 over R1. Just as a sanity check, does this change at all if that resistor R2 is included in our feedback network? Not a bit, right? All right, so hopefully I have expressed that it really doesn't matter whether you include that resistor R2 in your feedback network or not. Another way to think about it, would be, what if we actually had a designated load resistance R sub L? Would it matter if we accidentally included it in our feedback network? No, not even a little bit. So I just wanted to be clear about that. All right, so our open loop circuit for this guy, and I'm going to use this representation. Actually, I take it. I'm going to use this representation where R22 is included in our feedback network. So our open loop circuit is going to look something like this. Here we have RD. Here's our bias voltage. Here's transistor M2, here's transistor M1. IN. R11. Here's R22. Here's where we're taking our output voltage. So just like we did on Monday, I'm going to split this guy up into effectively 3 stages. Our first stage converts our input current into a voltage, which is going to be applied at the source of transistor M1. Our next stage is effectively just this common gate amplifier that generates the voltage that is used to bias transistor M2. And then finally, we have our third stage, which is transistor M2. So it looks like a source follower, right? So our overall open loop gain is going to look like Vx over In multiplied by Vy over Vx multiplied by Vout over Vy. So as Brian pointed out on Monday, he was absolutely correct. Our transfer function, if we are including, well actually our transfer function for our first bit here doesn't matter whether or not we're including channel length modulation in any way, shape, or form. So Vx over In is just going to be the resistance that our input current signal sees. So to the right, it sees R11, and looking into the source, it should see 1 over GM, and those two resistances appear in parallel. So we should have 1 over in parallel with R11. Now we have Vy over Vx. And I said on Monday that even with channel length modulation included, this is GMRD, but that's actually not correct. So that's the thing I wanted to go through this guy and work with you, because I don't believe in the textbook and in 335 we covered a common gate amplifier with channel length modulation included, because the book says it's too hard, but it's not remotely too hard, because we're going to do it and it'll take about 3 minutes. All right, so let me just slide down here. So to be clear, what we're looking at is effectively just this portion of our circuit. So here is Vy, which is the output of this stage, and here is where Vx is applied, right? So if I were to draw my small signal model for this guy, my gate is an AC ground. So this is my gate for 1. Then I have plus VGS1 minus. Here's my source for transistor 1, where I'm applying my input signal. Here is GM1, VGS1. Here's R01. Oops, excuse me. And here's RD. Anybody have a problem with this small signal representation of this stage with the effects of channel length modulation included? So our input voltage is applied between the source and the ground. So we can see that VGS1 is going to be the opposite of Vn, or in this case, I think I called it Vy or whatever. Let me just be clear about what's going on here. So to be consistent, this is Vx and this is Vy. So I'm going to redraw this guy in a circuits 1 style so that to me it's a little easier to analyze. I guess I can do it up here. No, I'll do it down here. I want to make sure I have enough room. So what that's going to look like to me, here's our voltage Vx, which, just to be super clear, here's VGS1. This node is then our source. This node is our gate. So connected to our source, we have GM1, VGS1, that current source in parallel with R01, and I'm going to skip a step and go ahead and do that source transformation that we did the other day. And so what that's going to look like is this. So the head of the arrow is connected to the source terminal, so that's where the plus sign should be. Here's the minus sign. So this should be GM1 VGS1 times R01 in series with R01, and then here is RD. This is our drain, and our voltage VY is the voltage drop over that resistor RD with respect to ground. So everybody okay with my circuits 1 drawing of our small signal model so that I know how to analyze it? All right, so it should be fairly straightforward here. I'm going to call this current IX, the current leaving the voltage source VX. And so I can see that I'm going to have negative Vx plus GM1 VGS1 R01 plus IX times R01 plus RD is equal to 0. If I substitute in the fact that VGS1 is negative Vx, what this looks like is Vx times 1 plus GM1 R01 is equal to IX times R01 plus RD, which means that our current IX is Vx times 1 plus GM1 R01 over R01 plus RD. Over here, we can say that our output voltage Vy is simply RD times Ix, which means that we have RD times Vx times 1 plus GM1 R01 divided by R01 plus RD, giving us a transfer function Vy over Vx is equal to RD times 1 plus GM1 R01 divided by R01 plus RD. So that's our transfer function with channel length modulation included. Like I said, isn't particularly difficult to analyze. I don't know why the book says it's too hard to do, because it very obviously isn't. So with that in mind, I will just directly substitute that in up here. 1 plus GM1, excuse me, R01 RD divided by R01 plus RD. V out over Vy. So we have a source follower with some load resistance, and we are including channel length modulation. This is literally an amplifier on the back cover of your textbook kind of thing. Like we've already dealt with this, so I'm just going to give us the transfer function directly. The only change that I make is they have the denominator as 1 over GM plus blah, blah, blah. I multiply through by GM so that I don't get weird, dumb fractions inside of fractions because I hate that. So with that being said, this is going to look like GM2 times R02 in parallel with R22 divided by 1 plus R02 in parallel with R22. Now I have all three of my gain stages, so I would simply multiply them together to get my open loop gain. Not going to bother. What's up, Brian? You're correct, yes. You're 100% correct. Yeah, so when I multiplied the 1 over GM through, I should have that GM there as well. You're 100% correct. Thank you for that. All right, so, and that would make sense because the source follower is effectively supposed to have a gain that's really close to 1. It's the transistor version of almost a unity gain buffer. All right, so I could multiply those three things together, no problem. Figuring out what Ri is. Of course, I didn't write it down. We did it the other day. So to figure out what Ri is, we would actually just kind of look at this guy again, and let's see. Oh, so it's buried right here. Right? If we no longer care what our output voltage Vy is, this is the exact circuit that we would use to analyze it, where we are looking for the ratio of Vx divided by Ix. So that's just going to be the denominator here divided by the numerator. So Ri is going to be R01 plus Rd divided by 1 plus GM1 R01, which is the exact result we got for our input resistance with channel length modulation included when we were looking at a similar input stage on Monday. Yes, you're absolutely correct. In parallel with R11. Yeah, 100% correct. Yeah, I think we called this Ri prime on Monday, but thank you for catching me on my bullshit again. All right, for our output resistance, what are we going to have? So here's something that we haven't done in a while, right? We're no longer measuring a current at the output, so we don't need to break open a short circuit and look at anything, okay? So our output resistance here is going to be looking in through the output terminal, and we're going to see whatever we see down in parallel with whatever we see up. So this should be fairly trivial at this point. Not Brian, what is it going to be? Yeah, 1 over GM2 in parallel R22. And we're done. That's the circuit analyzed. Now, just to be clear here, our gain, our open loop gain, this is positive, this is positive, this is positive. So this winds up being a positive feedback system because our feedback factor has a negative value. But the analysis method that we're using is still perfectly valid to analyze this guy. So I apologize for bringing the wrong example problem worked out to class. I guess the other one's sitting on my desk, but everything that we did in here is still applicable. So, all right, that is enough out of me for today, and I guess for this whole class, unless you got something else you want me to talk about. The part of the answer that we got from the last class that is wrong is this transfer function when channel length modulation is included. So if channel length modulation were not included, this is GMRD. When channel length modulation is included, this is what we should get, this is what we should replace GMRD with. Yes, sir.
So I have two questions.
Okay.
So one, EX over IN again, looking at that, if we include the channel length modulation, what's the 1 over GM? Or when it needs to be that R not 1
Because, yeah, well, shit, no, you're 100% right. Yep. So with channel length modulation included. So what the suggestion here is, I got to stop making these easy mistakes. All right, so the problem that we are facing here, we know that when we look in, we see this guy, right? So that should actually be our transfer function. Our transfer function, Vx over In, should just be Ri 100% of the time here. So you're 100% correct. So I'm just going to correct that to say Ri.
other one is looking at out.
Oh, yeah. Okay, so I see what you're saying. So with channel length modulation included, is it going to just be 1 over GM2? Yeah, no, that's a great question. So let's stop being lazy. That's the problem I guess I'm having is I'm so used to ignoring channel length modulation and I'm just saying it's going to be this, but we should test things. So let's look at R out again. And specifically, we're looking into the source terminal with our drain terminal shorted and our gate terminal short. Okay, so very good question. Yeah, so you're saying, I understand what you're saying. Because I've made so many damn mistakes, I'm going to go through it more formally just to make sure I don't make even more of an ass out of myself. Does that sound reasonable? I don't think it'll take any longer. The suggestion here is that this looks at what we're seeing looking into the source of transistor M2 is effectively identical to what we're seeing looking into the source of transistor M1, except we have an additional constraint. RD is shorted out because this node is also ground. So if we looked at this circuit where RD was set to 0, let me do it in blue up here. We'd have negative Vx minus Vx times GM1, sorry, GM2 this time, R02 plus Ix R02. So we have Vx times 1 plus GM2 R02 is equal to Ix R02. Therefore, looking up, I'm going to call it R0 up, is going to be Vx over Ix, which is R02 over 1 plus GM2 R02. Just double checking my algebra here. Sorry, this would be equal to 0. So that's just me doing KVL around that loop. So this first equation, everybody on board with. Okay. Then I move all my Vx terms to the other side of the equal sign, which is where I get a positive Vx from. It is 1 plus GM2 R02, so that makes sense. When I divide Vx by Ix, I'm going to have R02 in the numerator on the other side. I divide by that factor. Yeah, okay, so that's what I should see looking up through the source terminal, okay? That whole thing will be in parallel then with R22. So let's put that in. R02 over 1 plus GM2 R02 in parallel with R22. Thank you. Like legitimately, thank you. On the test, channel length modulation is going to be ignored, just to be clear. So, yeah, so that I don't make mistakes and so that you don't make mistakes. So. All right. Anything else? Yes, ma'am. Absolutely. Yes. You get an equation sheet front and back. I do not expect you to remember all this crap. So front and back handwritten. Yeah, 100%. For the love of God, don't memorize all this. Apparently, I can't do it, so I can't expect you to do it. Any other questions?
So we do what we did last class.
Yes. Yep. So if M2 were a PMOS transistor, what would change? Yeah, everything everything up to that third stage would be where we're determining V out over VY would be exactly identical. Okay. So then the only analysis that we would need to be doing is figuring out what that transfer function is. We could figure that out pretty easily. So we have a stage now. Here is VY. Here's VDD. Here's V out. Here's R22. So this is the source. This is the drain. So what kind of amplifier is this? And just for clarification, this is the gate. So we're applying an input at the gate. We're taking the output at the drain. What kind of amplifier is it? Common source. No degeneration or anything fancy. So in this case, with this as a PMOS, V out over VY is just going to be negative GM2. I don't know why I wrote R22 way down here at the ground symbol. Negative GM R22. What would our output resistance be? That's another good question, right? Or is that what you were about to ask, Alyssa? Yeah, okay. So if we looked at our output resistance, we'd still have, let me do it in orange, or yeah, let me do it in orange. Up in parallel with down. I feel like we can all strongly agree with down that is just R22. If that's not right, I'll give my PhD back. With regards to what's looking up with channel length modulation, so we have a mistake again because we're neglecting channel length modulation, and we shouldn't be. So what is it with channel length modulation not neglected? Just that in parallel with R02, right? For our resistance looking up with channel length modulation included, just to be on the safe side here, we have the following circuit. So our gate is grounded. Minus VSG2, where this is G2. Here's our source. It is grounded. Here's GM2, VSG2. Well, we know that VSG2 is 0 in this case, so that doesn't do anything. So this guy is just an open circuit between the drain and the source. We have R02, and from the drain, okay, and we're already looking, sorry, I was about to connect R22 to ground, but that would be double counting it in a sense. So when we look up, we see R02. When we look down, we see R22, And so the output resistance is just those two in parallel. That makes perfect sense because that's how a common source amplifier works. It's negative GM times the output resistance. We learned that back in 335. I just wanted to be real sure so I didn't make yet another mistake. So, yep, so that would fix it to be a negative feedback amplifier and all that kind of good stuff. And it actually makes the analysis much easier if we put the PMOS there. So, all right, any other questions?